that I thought I had 2 weeks after spring break before I went to a meeting, but I only have 1 week. Quizzes as I usually do. So I'm going to give you guys a quiz and also give you the quiz to help you prepare for the test. So it's open now. So if you want to do it now, that's fine. But I have it due at the week after. You've got plenty of time. So if you forget about it over spring break, you're okay. Because what's happening is that the quiz will be due at 5 p.m. on the 28th, and the reason it's due at 5 p.m. is because I'm releasing all the answers for you guys, so you have it to study for the test, for the test. So that quiz should help you, and I think it's got 15 questions. Some of them are very conceptual. Several of them are very related to the actual test that you guys will get in class. Then I've got the take-home portion. You guys currently can't see it yet, but it will become available on the 28th. And you'll go ahead and do it, load it back up to Blackboard, and it's due that Thursday of April the 4th. So the take-home test it'll release on Thursday, and it will be due on Thursday. And it's the circuit type problems. It's got some calculate the effective capacity or capacitance in there, but you should have plenty of time to do it and plenty of time to work through it. We're actually going to work another circuit problem today, and we're going to go over one more topic in this chapter. But the topic that we're going to go over, I don't have any test questions on it, because we'll see it again, but I don't have any test questions on it. I think you do have a couple homework questions on it. So the take-home portion of the test will be available the 28th, and then we will, when we get back on April the 6th, the 4th is a Thursday, so it's April the 5th when we get back, we'll be squared away. So Tonkawa, and I think that I'm not 100% sure if I've put the announcement out yet or not. I got everything to the facilitators and to the people that do all the ITV stuff. I got that done yesterday. I just don't know that I've put out the announcements to everybody yesterday. So you guys over in Tonkawa will take the written test on March the 29th. So Kelly, I need you to be able to proctor on March the 29th. On that side, and then you guys over here in Enid will take the test on April the 3rd, because that's the Wednesday. So we've got the test on one day, you've got the take-home test for the other day, and we're squared away. And when we get back, we'll start magnetism. I'll do kind of a rundown of kind of the topics that are on the test on Wednesday when we get back. And then we'll start magnetism on the Wednesday when we get back. So we should be in pretty good shape. And I think that gets us like only one class period off of where I wanted to be. So that makes me feel a lot better. Given our lovely weather situation that we've had this semester, it's been a little tough. But I think we've actually done pretty well. And it gives you plenty of time to, and what this is going to end up doing, I went ahead and made the in-class portion of the test worth 100 points, and I'm making the out-of-class portion of the test worth 100 points, so it should work itself out. So that'll get you guys kind of coordinated. All right, so now I'll go back to the document camera after we've had some good Friday fun. Yeah, I can tell you my day yesterday, my Facebook feed was filled with pies. Although Physics Today, just kind of a fun aside too, Physics Today, which I always call Esoteric Monthly, says pi is a flawed constant. And pi is just a ratio, right? Pi, the reason we get pi is related to the area of a circle, and it's just it's a constant. But it's not a constant, it's a ratio. There's another fundamental unit that we use, and we're actually going to see tau today, but we're not going to see tau as the constant tau. We're going to see tau as a time constant, And Physics Today says this is actually the better constant than pi, but pi is related to tau. So it's like tau over 2 is pi, or something very, very similar to that. So it's kind of an interesting little aside. So that's kind of fun for constants. People are arguing. And here's another one. Here's another Physics Today, which has started a great controversy. So let's look at the Earth. All right. So this is going to be the sun. And then we know that Mercury is out here. We know Venus is out here. We know Earth is out here. We know Mars is out here. And these are all the rocky planets. Once you get past Mars, we get the asteroid belt, and then we get the gaseous planets. And it turns out yesterday, Pi Day, is the anniversary of Einstein's birth. It's the anniversary of the discovery of Neptune. And it's the anniversary and Stephen Hawking died last year on Pi Day. Kind of an interesting trio of things that happened on March 14th. But going back to this, Physics Today said that which planet is statistically closer to us most of the time? So which is our closest neighbor? Common wisdom is it's Venus. Based on this radius, and the gap between here. The gap between the orbits is, we say that Venus is the closest neighbor. Well, a bunch of physicists went out there and did a statistical calculation, as physicists are wont to do. And they said, nope, it's Mercury. But here's why. If you look at the orbit of Venus, there's a lot of times that Venus is on the other side of the sun from us. And if you look at the orbit of Mercury, Mercury goes around the sun a lot faster, so we're closer to Mercury more often than we are with Venus on the actual rotation. So if you look at it on an average statistical basis, and the other part is we talk about the planetary plane, which is another one of the reasons why Pluto was demoted, because Pluto's orbit goes like this. It's not in the planetary plane. It's kind of cattywampus. That given, even though we think about it as being in a plane, it's not really in a plane. So between all of that, with Venus being on the other side of the sun frequently from us, and all of that part of it, turns out statistically more often Mercury is closer to us on average. Kind of an interesting, which spurred all kinds of arguments, and I'm sure letters to the editor of Physics Today will go on for months, because they're like that. All right, so let's get back to circuits, something that we can actually sink our teeth into. So we're going to do a circuit, and we're going to play with this circuit a couple of different ways. So this is going to be 6 volts. This is 6 volts. This is 5 ohms. This is 10 ohms. This is 10 ohms. And this is 15 ohms. Now, and essentially what we want to do is we want to figure out the current through each of the resistors. Okay, so it's kind of what we want to do is we want to find the current through each resistor. All right, so let's put ourselves some reference points because it'll make life easier for us. So I'm going to do A and B, and I'm going to do C and D. So those are my reference points that I put in. Now, the first thing I'm going to do is I'm going to simplify this. I'm going to simplify that. So this is kind of a nice, good one to kind of review some stuff. Because that essentially are just two resistors in parallel. And if I've got resistors in parallel, I can remember that the equivalent resistance is going to equal 1 over one of the resistors plus 1 over one of the other resistors. That's going to give me 15 plus 10 150ths. If I do my fractions. And that's going to give me 25 150. But to get REQ, I have to flip it. So I get 150 over 25. That's going to equal 6 ohms. So I can redraw my circuit. So let's redraw the circuit. Not a very good resistor, but we all know what I'm trying to do. So now my circuit looks a little simpler to work with. So that's 5 ohms, 6 volts, 6 volts, 10 ohms, but now that's 6 ohms. So now I'm going to put in my currents. So I'm going to put in an I1, I'm going to put in an I2, and I'm going to take out an I3. So I'm going to use a junction rule here. So I have I1 plus I2 is equal to I3. Now I'm going to do a loop. So this time I'm going to do the loop C. We got A, B, D. So I'm going to do the loop D, C, A, B, D. So I start with the 6 volts, and I'm going with the current there, and I get a minus I2 with a 10 ohms, and I get a minus I3 with my 6 ohms is equal to 0. Well, yeah, okay, that's this one. So there's that one. Now I'm going to go over here and I'm going to write this loop. So now I'm going to go D to C to D. So this is going to be 6 minus I1, 5 ohms. And then I'm going backwards across this one, so I've got to change my direction. I2, 10 ohms, minus 6 has got to equal 0 because I'm going against the current. I have to switch the directions. This one is fortuitous to us because I've got a 6 minus 6. Yay! And now I've got a minus 5 I1 plus 10 I2 has got to equal 0. And that's going to tell me that I1 is equal to 2 I2. So I get a really simplified equation right away. So that's really, really helpful. So if I look at that second loop, that equation right there, I'm getting, so I have I1 plus I2 is equal to I3. I have I1 is equal to 2I2, and I have 6 minus 10I2 minus 6I3 is equal to 0. This is kind of fun because I can take I3 and put it in terms of I1 and I2, so let's do that. So I'm going to take 6, 10, I2 minus 6, and I've got I1 plus I2 is equal to 0. But we know that I1 is in terms of I2, so I can do that. So I get 6 minus 10 I2 minus 6, and I'm going to put in 2I2 plus I2 is equal to 0. So I get 6 minus 10 I2 minus 12 I2 minus 6 I2 is equal to 0. That gives me 6 minus 10, 12 is 22, plus 2 more, minus 28 I2 is equal to 0. And I get 6 is equal to 28 I2. I2 is equal to 28 divided by 6. And if I punch that into the calculator, which is not one of the ones I did immediately, 28 divided by 6 make sure that's okay, so 6, okay. What's I2? That's 3I2, that's 18. I get 4.67. It's just not agreeing with my notes, which is why I'm trying to figure out what I did. My notes could be wrong, so. Yep, that's 3I2. All right, we'll go with it. We'll see what happens. That's what I get. Make sure so I got I2 is equal to 6. So I1 is equal to 2I2, which is now times 2 is now 9.33. And then I3 is I1 plus I2, which is going to be plus 4.67. Is going to be 14.00. So that part we got. So I've got I1, I2. So now we got to go back and take care of our 6 ohm resistor, which is really a parallel circuit here of 10 and 15. Okay, it's a parallel circuit of 10 and 15. I can do it one of two ways. I can go in here and make this, say this is an I4 and then this is an I5, or I can go back and do it the way we did it earlier in some of the earlier problems. And so that's the way I'm going to do it now, is we're going to find, the first thing we're going to do is we're going to find the voltage across there. And that voltage is equal to IR. And we know that the voltage through the 6 ohm resistor is I3. So this now is voltage is equal to I3 across the REQ. So my voltage is going to be I3, which is this one. It's going to be 14 times my REQ, which was 6. Which is going to be 6 times 14. It's going to give me 84. And so that's 84 volts, which doesn't seem right when I start out with only 12 volts in the system. So I think I've done some arithmetic wrong somewhere. I'm going to go back here and look. 6 I10 minus 6, that's right. I3 is going to be 3I, that's what's wrong. No, that's right. I2, I1, okay. I3 is equal to 3I2. I1, that's what's wrong. I did do a mistake. I1 is 2I2. Or I1, yeah, I1 is 2I2. No, that's right. That's 9.23. Right there. I'm going to go back to this one, because how I did it in my notes was like this. I got 6 minus 10I2 minus 6I3 is equal to 0. So I get 6 minus 10I2 is equal to 6I3. So I3 is equal to 3I2, because 2I2 goes there, plus 1, so that is right there. Well, that's where I made a mistake in my notes. No. So we got that. So I'm going to divide both sides by 6. So I get 1 minus 10 over 6I2, and that's going to give me 3I2. That's how I did it in my notes. So now I get 1 is equal to 3I2 plus 10, 6I2. And that gives me 4.67 I2. It's equal to 1. And so I2 is equal to 1 over 4.67, which is equal to 0.214 amps, which that number looks a lot better than my other one. So I'm still trying to figure out where on earth I screwed up there. But I did something wrong because, and the reason is, there's no possible way to have 84 volts in a system that I only have 12 volts in there. So something's definitely wrong, and I don't know where I made the mistake today. It's Friday, and it's early in the morning, and I don't know where it is. So now, if I go back there, I1 is equal to 2I2, which is going to give me 0.429 amps. I3, which is 3I2, is going to give me 0.642 amps. So those are definitely correct. Because now when I do my voltage across the 6 amps, That's going to be my voltage is going to be I3 across the 6 amps, or I3 across the 6 REQ. That gives me a voltage of 3.852 volts, which makes a heck of a lot more sense for that circuit. Because now I've got 6 volts here, I've got 6 volts here, and going across there, I've got a drop in voltage, so I've got to have that drop in voltage there. That makes a heck of a lot more sense for my circuit. So if I do that, now I can go back and do V is equal to IR, except now it's V across, divided by R is going to be I. So now if I do that voltage, it's 3.852 divided by 10 for the 10 ohm resistor, and that gives me 0.35 or 3852. And the other one is my 3852 divided by 15, which gives me my 0.257. So now I've got all of these voltages, or all of these. I've got I1, I've got I2, I have I5 and I4. If I draw it in there. And then I've got I3 right there, but it's not going across a resistor. And I had confidence that this answer was correct because you can check it. You can totally check it because I can do this loop. Okay? So this loop here, so this is my 10 volts and this is my 10 ohm and my 15 ohm. And we put in the system that I had an I5 and then I had an I4. And what happens is that I have I3 is equal to I4 plus I5 coming in at that junction point because I3 came in there. So I have that one right there. Now let's do this loop. So this loop I'm going to get a minus 15 I4. Then I'm going to go around the loop and I'm going to go backwards across that one. So that's a plus 10 I5 is equal to 0. So if I do this, I get 15 I4 is equal to 10 I5. And that means I4 is equal to 10 over 15 I5, which is 0.67 I5. So I can go in here and I can say that I3 is equal to my 0.67 I5 plus I5, which is going to be 1.67 I5. And that means I3, when we figured out I3 was 0.642. So I get 0.642 divided by 1.67 is going to equal I5. 0.642 divided by 1.67. It gives me 0.384, and that's compared to what I got as 0.385, which is really just how much I'm carrying significant figures. So you've got a means to check it because you've got a couple of ways to come up with the same answer. Now you also know why I give you extra time to do circuit problems. Because even if I work it out, you can still mess it up. Okay. So let's look at the next thing. The next thing that we have to do, and it's the very last thing in this chapter, is now we want to build, because circuits aren't just resistors, and circuits aren't just capacitors, and circuits are a combination of things. So one of the things that we have to look at is what happens in a circuit that looks like this. So I have a switch. Now, if we look at a light board, and you guys have done it in lab, let's draw the circuit a little differently. I'm going to put my little incandescent light bulb in here. Okay, so I have a circuit that looks like that. These are our incandescent light bulbs. If I throw the switch, the light bulb immediately glows, right? You get that immediate glowing of that light bulb. Now, if I throw the second switch, both of these immediately glow, but what happened to the light bulbs? They got dimmer, right? They got dimmer when I threw that switch. So we know that at least, and these are resistors, because those little incandescent light bulbs that we work with in the lab and on a flashlight, they're about a 10 ohm resistor. So we know what happens when I flip the switch. Now you guys did this in lab too. You actually did this. You had a capacitor and then you had a resistor and you flipped the switch. What did you notice? Take the old camera flash, or the old flash camera. If I have one of those little wedding cameras, those little Instamatic wedding cameras, and I want to take flash and I flip the switch, we hear the high-pitched whistle, right? And then all of a sudden we get the little blinky light that tells us that this capacitor is charged. So when I do this, what we notice right away is the light doesn't immediately come on. It takes it a little bit, because if I'm thinking about what's happening, because we know what happens, and we're going to think about it in reverse because Ben Franklin was wrong, is as I send charge, I've got to charge up this capacitor before my circuit works. So what happens is I'm going to get a time delay. And you actually probably saw it in lab, you just don't remember because that was like 3 weeks ago. So you actually saw a time delay before I could actually see that light flash, or that little light start coming up. Now the other thing that happens is that when I open the circuit up again, the light immediately doesn't turn off, but it slowly dims. So there's a time delay as the capacitor discharges. So I get a delay based on how long it's going to take to charge the capacitor, and I get a delay on how long it takes to discharge the capacitor. And so what we can look at is, if I'm looking at the charge, in one case, it's going to take a long time to get the charge up there, and it turns out that one case, it goes like this, where I use the natural log of the time that it takes divided by the resistance in the circuit times the capacitance in the circuit. And on the other case, the charge is going to discharge based on that situation right there. And what's happening is, one case, if I'm looking at charge, okay, now be careful here when we're looking at charge, and remember that charge is the capacitance times the voltage. If I'm looking at charge, it's going to fill up, and I can plot that charge, and it's going to look like this. And so these equations come from the graphs that we actually physically see. And it turns out that this little piece here, the T divided by RC, is going to be related to a time constant, and we're going to call it tau. That's related to the RC. And that's going to base on how long it takes to get to 63%. Conversely, if I do the discharge, it's going to fall. And that time constant is going to be based on that 63%. So I can sit here and explain it, but it's easier to kind of look at it. So we're going to actually look at it because I found a pretty good representation of how it looks at. Okay, that's bizarre. And that I've actually plotted. So you could do it a couple of different ways. There's the handy dandy thing. So back here in week 9, I've got a simulator that you can play with and put in whatever circuit you want and put it together. But I felt like this guy actually put together a nice presentation on it and looking at the circuits. So we're going to watch this because he's going to actually show and look at the voltages and everything associated with it. So if I can go there. See if we can get volume. Okay, so we got that part, I always love the rooms because the rooms are always a challenge. See if we can get that. Okay. See if I can go here. Okay, that's full on. Okay, there's no volume on that one. No volume on that one. I'm going to add volume here. Let's see what we get. That's better.
I'm going to demonstrate here the charging and discharging of an RC circuit. The first circuit we're going to examine is a 10-volt battery which fills a 100 microfarad capacitor through a 100 kilo ohm resistor when I close the switch. Now the combination of the resistor value and capacitor value, 100 kilo ohms multiplied by 100 microfarads, produces an RC time constant of 10 seconds, which suggests that this capacitor will fill to 63% of its final value, namely 6.3 volts, after a period of 10 seconds. So I'm going to demonstrate that and count it. We can examine the rising voltage on this DC voltmeter, and we'll also be able to see the effect of the rising voltage on this oscilloscope. Down here we have another switch which, when we close it, will discharge the circuit. So after we have filled the capacitor, we're going to empty the capacitor again. This time we're emptying it through a resistor which is 10 times smaller than the 100k resistor, and it produces a time constant of 10k multiplied by 100 microfarad, which is effectively 1 second. So we should see the capacitor fill over a period of 10 seconds and empty over a period of about 1 second. So we've just run the simulation, and as soon as it starts, then we'll close the switch, and immediately we can see the voltage across the capacitor increasing. We're running here at about 7 seconds, 8, 9, 10 seconds. So you can see it's gone up to this value. Meanwhile, over here we can see the oscilloscope, the voltage on the oscilloscope rising. In this case here, rising at 2 volts per division. So we have 1, 2, 3, 4, almost 5 volts, 5 divisions, which is 10 volts. So we can see at this point here, the capacitor is almost full. There's very little change in the voltage across the capacitor, as we can see here. Now, if we click that switch open, capacitor holds its charge because it's nowhere to empty the charge at the moment. So we see it's got 9.976 volts across it. And in this case here, you can see it has almost 10 volts on the oscilloscope. So we're going to discharge them by closing this switch here. And we're going to see it decay very rapidly compared to how it fills. If we close this switch here, and then suddenly, in almost a second, the voltage is dropped, and we'll have seen this voltage drop here again. So if we open this switch once again, we'll charge the circuit and just examine it on the oscilloscope so we can see it as it's charging there for. So it's slowly filling up. So that's 7 volts there. And we're at 8 volts. So it's just trickle feeding into the capacitor at this point here. So again, we'll open that switch. The capacitors, there's 8.87 volts across the capacitor. This time, we'll close the switch and then we'll focus on what's happening on the oscilloscope. We'll see it decay very quickly. And we see the voltage then across the oscilloscope decay very quickly. Here's an example of an online simulation of an RC circuit charging and discharging. So just first in reference to the website.
That's a Taiwanese website, by the way. I tried to find it and I couldn't.
Thanks to those for this simulation. So let's look at the circuit here. First we have a resistor, which is a 100 kilo ohm resistor. We have a 100 microfarad capacitor, and we're feeding with 10 volts. So what we see here is we have a battery, which will charge this capacitor when we close this switch around in this direction here, through this resistor, a 100K resistor, and then charge that capacitor. What we're going to look at here is we're going to see a simulation of a plot of the voltage across the capacitor as it charges. The capacitor will rise. We're also going to plot the current that's flowing in the circuit, the charging current, which will start off initially very high because you've got an empty capacitor. And then as the capacitor becomes fuller and fuller and fuller, and the difference in driving voltage between supply voltage, the 10 volts, and the capacitor voltage, that will decrease, so there'll be less motivation for the current to flow, and we'll see it decay. What we're going to do is when we click this red switch here, we're going to start charging the capacitor, and then the second time we click it, we'll discharge it. So we just do this and follow the flow. So click on this, and this simulates the actual flow of the electrons. But just look what's happening here. Follow the red line. This is the capacitor charging, and the blue line is the current that's flowing in the system, which is decaying. So now we see this exponentially saturating curve here. So the capacitor now is reaching the point at which it fills quite slowly now. And the reason it's filling quite slowly is because there's only a trickle of current going in here. So as it runs on after, in this case here, the time constant for the circuit would have been 10 seconds. That's 100 kilo ohms multiplied by 100 microfarad gives 10 seconds. And what we'd see here is that after 10 seconds, it would have reached about 63% of its value, which is 6.3 volts. Whereas 50 seconds, that's 5 time constants later, we can see that the thing is almost 99% full, and there's only a trickle of current. So what happens is the capacitor continues to attempt to fill with the smallest drop of current flowing into it, but there's almost nothing happening. Now at this point here, we will change the position of the switch, and we'll see the capacitor starts to discharge, in this case here, in the opposite direction. As you can see, the discharge voltage of the capacitor starts to discharge initially very quickly, and at the same time we can see the current. Now it shows under the line here because the current is going in the opposite direction. So again, the current is decaying from a high negative value to a low value, and again the current is falling to a trickle. We can see it falling to a trickle here as the capacitor voltage settles down to be almost In this online simulation, which again is thanks to Frolstad.com, we're going to look at a circuit implementation of an RC charging and discharging circuit as it's used to drive a very standard chip called a 555 timer, which can be used in many timing circuits. So we just reset here, and again, if we just look at the waveforms that are appearing here as they unravel, we're going to look at the charging of a capacitor, which charges with the exponentially rising arrangement, and at some point later starts to discharge. And if we just follow this for a moment, we'll see a charging and discharging. And every time it changes direction, you'll see an output from the circuit, which is a digital 1 or 0. So we get this rectangular waveform which comes out of the circuit. Now if we just look up at the components here, this is the output, which as you see, it's changing color every time the output switches from a high to a low. So that's the voltage that we're looking at here. If we look at how the circuit operates, this circuit operates on the basis that we charge the circuit. It's this point here. We're charging this circuit. We're charging this capacitor through both of these resistors to a 10K in series with another 10K, filling this capacitor here. When the direction of the capacitor or the capacitor voltage changes, what we find is that we discharge this capacitor, but this time it's only discharging through a single resistor, through the 10K resistor. So its charging path, the resistance in the charging path is twice the resistance of the discharge path, which is, if we look down at this waveform here, why we can see that the length of time to charge is a lot greater than the length of time to discharge, simply because of the arrangement of the respective values. So in this case here, for example, we see an output waveform which is it's high for twice the amount of time it's off, and this is called a duty cycle of 66%, so it's on for 2/3 of the time. Or it's also termed to be a mark-space ratio of 2:1, where we classify the mark as the period when the output is high and the space as the period for when the output is low. Now therefore, if we choose to specify our component values at any particular level here, we can determine the period or the charging period for this circuit here. So for example, in previous examples we have looked at, if we had a 100K resistor and a 100 microfarad capacitor, that would mean such a capacitor would fill in to 2/3 of its value in about 10 seconds. So if we have, in this case, a 200K resistor, a 100 microfarad capacitor, that would take 20 seconds for it to fill to 63% of its value, which is almost 2/3. Now you might ask yourself, why does it switch on the way down? Well, the internal components of a 555 timer have a set of what's called comparators, and they set a threshold value of 2/3 and 1/3 of the supply voltage. And any time the capacitor voltage exceeds, as we see down here, when it exceeds 2/3 of the supply value, which is 6.67 volts, it then discharges the capacitor. When that falls down to 1/3 of the supply voltage, which is, for a 10 volt supply is about 3.3 volts, then the comparator switches and starts a charging cycle again. So you have what's called a free running oscillator, where you're charging and discharging the capacitor, and that the timing arrangement is determined by the component values for the charging cycle, R1 plus R2 multiplied by the capacitor. And for the discharging cycle here, the value is determined by this resistor here, R2, and the capacitor value. Thanks for watching this reusable learning object from Lemo.com.
So the idea behind those timing circuits are, if you're wanting to control a process, which we do in the refinery a lot, you need a timing circuit to be able to do it. So it's going to click on, click off. So think about when you if you've got your stove and you want to keep something at a constant temperature, you're going to have to turn on the resistor so it's going to stay warm, but you want to turn it off so it doesn't get too hot. So you can have a timing switch in order to generate a particular process. Could be a fan, could be a fan cycle, could be a lot of different things. And so from an electronics point of view, you actually build these timing circuits. And so you can see why somebody might want to put in a timing circuit into the system. The key here for us right now is to realize that as soon as I put a capacitor in, I'm building a delay into my system. So I'm going to be able to use a delay of some sort to be able to control things for other circuits. And now we'll start building on that coming on Wednesday when we get back to look at, start looking at magnetism, because our other circuit, our other component that we need to have is based off of magnetic field. So you all have a great spring break. If you want to work on the quiz over spring break, it's out there. But otherwise, you have fun spring break, and we'll see you Wednesday after spring break.